First, let me tell you why the hell you should listen to me and who I am. I started as a quantum physicist and worked in quantum experimental labs for 10 years or even more, building all this fancy stuff like quantum computers that can break modern cryptography within a second, and quantum cryptography that is perfectly secure. So small spoiler, quantum cryptography is not safe as soon as it goes to the real world implementation, and quantum computers are not there, and probably they will not appear for another 10, 20 years. Bitcoin was my hobby first, and I started by building my own hobby project, a hardware wallet, just because I didn't really like what was at the time on the market, and there was no code card, and I was extremely scared to put my funds with any kind of connection to my online computer. So it was something very simple, Arduino-based SD card air-gapped hardware wallet, and then there was another revision where I included the SegWit and QR codes after the Jimmy Course seminar, actually, programming blockchain. And then we went to the hackathon, where we built a kinda Lightning hardware wallet, but not really, but what you can do in 2 days, you know. And then finally another revision and so on. And in Lisbon, I met these two guys. And we actually founded the company, and I was able to quit my job in quantum physics and started working on Bitcoin full-time. So this was really cool, and finally I can start working on the real security with the security lab based in Munich, and like building secure hardware. So I want to share with you what I learned during this pretty long journey, and one important thing that I understood is that everything basically can be hacked. And the question is, what is your security model? For instance, how inconvenient you can make your, you're willing to make your private key management system to get some extra security. And it's totally fine to have a few €100, for me at least, on my phone, and even if it got hacked, it's not a big deal. As soon as it touches my salary, it's already more like I want something more secure, like a real hardware wallet, and yeah, life savings, Shamir secret sharing scheme, multi-signature, and all this kind of stuff that is probably very inconvenient, but life savings, right? But you need to also remember that the attacker actually also needs to take the same trade-offs. So he wants to optimize the profits from the attack. If there is an attack that is very easy to implement and that is extremely massive, like a software bug in communication with a hardware wallet or just hacking your computer remotely, then, well, you're screwed. And it is the attacks that are permanently kind of monitored, and if you get the malware on the computer, it probably will check all the possible kind of normal positions for the files that are stored in your private keys. Then another attack that is more or less easy to make, to implement, is the supply chain. So the only thing that you need is access to the DHL packet shop, and you replace your hardware wallets with the different ones, and well, also pretty massive. And the evil-made attack is, I would say, the most targeted one and the most expensive for the attacker. So we just need to remember both of these axes and put ourselves somewhere here. So how much do we value our kind of savings, and what trade-offs we can make. So regarding the software attacks, what can be done in principle? So obviously, storing the secrets on the computer is pretty bad, and this is what the attacker needs to run on your computer on your Lightning node to get the secret from C-Lightning. Then, yeah, the bugs that's happening because you realize the data, processing the data from the user also can be, well, pretty large attack surface, and it's very easy to shoot yourself in the foot, yeah, not in the head, with this thing. But plus, you also need to remember that kind of cryptographic libraries also can have bugs. I mean, the Heartbleed was on OpenSSL, and it kind of affected the world quite a lot. But yeah, my favorite one and the most hilarious one is how the Sony failed to defend their PlayStation 3 systems. So basically, when you're doing the signature, you need to sign the message with your private key, and you also use a random number as a blinding factor that allows you to generate the signature without exposing your private key. And these guys, they just reused the same blinding factor for all the signatures, meaning that if you have two signatures of two kind of different games, then you have two linear equations with two unknowns. You derive the private key of Sony, and then you sign any game you want. So this was quickest hack of the game console, I think, in the history. Then regarding the supply chain attacks, currently the chips that kind of provide you with wireless functionality, like connecting to mobile networks or internet, Bluetooth, and so on, they're pretty small. I mean, yeah, so you can easily just take your hardware wallet, put hardware implant in there, and then close it back. So that is pretty bad. Another option is you talk to a Chinese factory, and for some reasonable amount of money, they will make the chip that looks exactly the same, had the same markings, but uses slightly different functionality. For example, it can it replaces your secure element or something with not very secure one that uses a slightly changed signing algorithm to leak your private keys to the blockchain with the signatures. And yeah, I recently wrote a blog post about that, and we can talk afterwards if you're interested. And finally, if the attacker really wants your bitcoins and he gets your hardware wallet, then he can use all the tools that are available and to do the voltage glitching, like the one this thing was shown in the C3 Leipzig wallet fail talk, how to extract the firmware from Tether. Then they can use decapping tools to get access to the microcontroller on the silicon level, and then you can do very many different things, like shining with a laser or exposing with ultraviolet light, and do all kinds of fault injections. And also you can do the side channel analysis to see how your wallet operates during the, well, maybe not signing, well, just during the operation, and get some data from it. So again, developer conference, so you're not scared of the code. So this is the most terrible piece of code that I've ever written. But in principle, I can imagine that something like this can be deployed to some unnamed hardware wallet. So basically, this function just checks the PIN of the user. And this is when you get the hardware wallet, this is kind of your last resort, last defense. Because if you pass the PIN check, then you can sign any transaction and you can get all your money from the hardware wallet. And what it does, it basically has a pin counter that increases when you enter the wrong pin. Then you have the right pin, the space for the entered pin, and the mnemonic itself. So if we look at this function that checks the pin, and in particular this one. So one quick note, C is still the most common language in embedded development. So even though there are MicroPython and Rust, most of the systems are still written in C. And C was designed pretty long time ago, so when people didn't really think about the security, so it has a bunch of built-in functions that it is very tempting to use them out of the box, but but you need to remember that many of them are not very secure. For instance, scanf. I think that every conference like Black Hat, DEF CON, or whatever, have one talk that is talking about either this function or something very similar. So the problem is that it takes the user input and stores it in the buffer entered pin. The problem is that it doesn't check the amount of the data that we get from the user. So if we look at the memory location of our program, then we have 4 bytes of the entered pin, 4 bytes of the correct pin, and what we do here, we compare these 4 bytes to these 4 bytes. So if we enter the wrong pin, then obviously it's wrong, and then we increase the counter and stay in this infinite loop. But if we enter 5, 6, 7, 8, then 9, 5, 6, 7, 8, then what happens with this function, it just overrides the rest of the memory, and in particular, it overrides the correct pin. And after that, you kind of compare them, and they're the same. So this is a very easy implementation bug that I think that's, well, used in many capture the flag challenges, so people kind of know about that, and there are obviously ways to secure that. You just need to use a secure version of the function that checks how many bytes of memory you can overwrite with the user data. Something very similar. In this case, we failed with allocation of the memory for this message that prints out how many times we kind of entered the pin wrong. So in particular, it is enough, just enough to enter to print this message. But as soon as we enter the pin incorrectly 10 times, what we get, we have 1 extra byte in the string. It moves. The new line character overwrites the end of the string. And then instead of printing you entered the wrong pin 10 times, you print and you entered the wrong pin 10 times, and then the whole mnemonic that you have. So also pretty bad. But yeah, obviously, if the engineers are good enough, they can fix all these kind of things. And in particular, you just allocate enough memory to not to overwrite these kind of things for any reasonable amount of pin enters. Another thing that can happen if you fail to program the thing correctly. If you're using, for instance, the string compare function, the problem is that how it works, it checks the first bytes of the pins, and then if they're different, then it returns to the failed case. If they're the same, then it will start comparing the second one. So here you can easily make a timing attack. So you just brute force, instead of brute forcing all possible pins, you start with the first digit, you try like 1, 2, 3, 4, 5, and so on. As soon as you see a tiny, slightly larger delay between the pin and the response, then you know that your first digit is correct. Then you repeat it with the second one, the third one, the fourth one, and instead of brute forcing 10,000 different pins, it's enough just to brute force like 20. So obviously, if something is touching some secret information, you really need to use the secure version of the functions. In particular here, we need a constant time function to compare the strings. Or ideally, you don't work with the strings, but yeah. So now it kind of looks more or less safe. But now let's talk about the microcontroller that is running all this stuff. So some of the hardware wallets use a general purpose application microcontrollers. And the problem with them is that these microcontrollers are designed, not really designed for security. So they have, from the very beginning, certain assumptions about the environment that they are operating in. In particular, they're expecting a certain level of the voltage between, let's say, 2.7 and 3.5 volts. And they're expecting a certain clock reference that is going up and down with a certain frequency. And if this is not the case, and if the attacker manages to change this environment slightly, then you can have very weird bugs. In particular, during the clock cycle, what happens on the assembler level, you change the instruction pointer to the next one, and at some other time, you actually execute the instruction. And if the attacker lowers the clock voltage a little bit earlier before that, then what can happen? Your instruction pointer already moves to the next instruction, but the instruction itself wasn't executed. And meaning that you basically can skip any instruction of the microcontroller. And the same can happen with the voltage glitch. So you just lower the voltage at a certain level and you skip the instruction because below a certain threshold, you get the undefined behavior. And for the attacker, undefined behavior is actually a good thing. So what can happen here? We can skip, for instance, wait millisecond part, and then we can brute force the pin any number of times. Or we can even exit the while loop completely. So we can just make this glitch to go directly here. Then another thing that can happen, When the microcontroller is trying to print something, what it does, it checks the length of the string and then prints the characters from the memory from here to here. So if we do default, make this calculation of the length incorrectly, such that it is some random number, then what we can get, not just the string that we are trying to print, but actually the string that we are trying to print plus some arbitrary amount of the memory that microcontroller has. And what can happen, maybe your mnemonic isn't there. So you can print out your mnemonic. In general, this is the problem of the application microcontrollers. Then another thing, if the attacker really wants to get to your funds, what he can do the decapping of the chip. So basically, you take the chip, you put it into the makerspace under the laser cutter, you remove parts of the chip, like the plastic parts, then you kind of get already almost all the plastic out. Then you put a few droplets of the nitric acid on top, you heat it up to something like 100 degrees or so, and at the end, you get a chip like this, and you can observe it with a microscope. If you know the structure of the microcontroller, then you can see the positions of the secrets, the input and output buffers of your registers of your microcontroller, and basically everything. And what you also can do, for instance, you can find the region of the memory in here that is responsible for storing of the pin or storing of the pin counter, and you can hit it with a laser and or shine with the ultraviolet light and protecting the rest parts that you care about with just a nail varnish. So it is really cheap attack, actually. And then you can erase parts of the memory. In particular, you can erase the part that stores your pin, and then your pin will be 0, 0, 0, 0. And yeah, you know the pin, you pass the check, and that's it. You can also erase the pin counter. So these kind of attacks, well, it's pretty hard to deal with them. Secure chips have very many different countermeasures against that. The problem with them is that they normally require NDA. And in Bitcoin community, we don't like NDAs, right? So we kind of prefer to keep everything open source. But still, it somehow became an industrial standard, and I hope that we can change it somehow and develop something open source and still secure. But right now, we have a few options for the countermeasures. So for the software attacks, oh, I still have some time. That's great. I didn't expect that. So for the countermeasures, to prevent ourselves from doing some stupid mistakes, we definitely should use a memory-safe languages. So the industrial standard, again, is a Java card OS. So this is basically the Java on the microcontrollers. The source code of this thing is completely closed source, but to kind of get you some feeling of the security, they provide with a certain certification level. So basically, you trust that the manufacturer implemented the OS correctly, and then it was checked by some, I don't know, security labs. So then another thing that Trezor, for instance, is using is MicroPython. Really great, because it basically it is memory safe, but it is a pretty new language, and currently number of microcontrollers supported is not very large. Then what I'm really excited about is embedded Rust. Rust is the language that was from the very bottom designed with the security in mind, and it actually helps a lot in this kind of things. And there is even an operation system like TOCOS, I think it's called, that allows you, so it is written in Rust, it is running in the microcontroller, and it allows you to do all kind of memory separation, memory kind of checks, and things like that. So it is really good platform to work on. Then regarding the side channel attacks, you still can do something with the application microcontroller. You can do much more with the security-focused ones. So what the industry normally uses to get rid of the side channel power analysis, let's say, they add some random noise. So together with your cryptography function, some arbitrary noise is enabled and decreases your signal-to-noise ratio by a lot. Then you can use random timing such that instead of just constant time functions, you introduce some random delays and kind of calculate different parts of your crypto algorithms at different times. So this also helps a lot. Then modern microcontrollers have threadings. So if you have threads, then basically your timing is unpredictable, more or less. It also helps a lot because actually all these kind of attacks, they require from the attacker really, really precise timing. So again, on Wallet Fail talk in Leipzig, they said that they were trying to hack, to glitch Trezor for a few months, I think. And well, timing really matters there. So these are very simple options to make the attacker's life much harder. And finally, Faraday cage, for instance. So this is what is used in industrial secure microcontrollers. So basically, you cover the whole thing with a cage that not only prevents you from kind of electromagnetic wave emissions, you also monitor constantly the state of this mesh. So as soon as the attacker tries to decap the chip to kind of somehow get to the semiconductor level, they damage this mesh, and well, you see that, you write the flag that the device was tampered, and for instance, you wipe all your secrets. Then, with the glitching watchdogs, yeah. So again, this is pretty hard to get on the general purpose microcontrollers. The security focused ones, they have it out of the box, but the question is how you make them work. So either NDA, and then you need to produce something in the large scales, or you're relying on something like Java Card OS that you don't know really what is running on it. And then also you can have sensors, like on the silicon level, whenever you try to decap the chip detects the temperature change or the ambient light increase, and also raises all the secrets. And obviously, against the voltage and clock glitching, you can just put the reference inside the chip itself. So this is also pretty most common practice. And now the very hard part, the tampering and hardware implants. So commercial HSMs, the hardware secure module, they use a very fancy and very ugly way of doing this. So basically, your board has a battery, and it is constantly connected in the data center to the thing. And it has a mesh, and it runs the current through this mesh all the time. And it measures kind of if this mesh was damaged or not. And as soon as you try to drill even a tiny hole in it, you actually get detected, and all the secrets are wiped. The problem here is that you need a battery all the time, and also it is very fragile. So for normal hardware wallets, it's not that convenient, especially you probably don't want to lose your funds if you just dropped your hardware wallet and it just hit the floor. So there are easier way. For instance, you can just include the photodiode on the board, and even though it doesn't give you an ultimate security, it still increases the attack cost of the attacker. So he needs to know that there is a photodiode inside that's constantly monitoring if the box is open or not. So again, on that scaled that axis that I showed in the beginning, you are moving the cost of the attacker forward to the more expensive ones. And yeah, that's more or less it.
We got time for like a question or two.
I think
if anybody want to raise their hand, I'll
questions.
walk over with the mic. Right.
Yep.
In the back. Feel free to stand up.
So you mentioned constant time algorithms for your crypto versus random timing. Could you talk a bit more about the difference between the two and the trade-offs between using constant time versus random delays?
So normally you have to use constant time functions, but so basically you use a constant time crypto functions at the very beginning, and then on top of that you add some random timing by including into this constant time function some random timing. So in practice, I didn't really see implementations of the random timing for the normal crypto algorithms because everyone is using constant timing. And the things that are used in the industry, unfortunately, I don't have access to these things. But it's just like I talked to the guy who knows the guys who implemented the random timing in there. But for instance, the threads are probably good things to do. And one easy implementation of the random timing, I would say, when you're calculating your Bitcoin seed from the mnemonic, you need to do this PDKF2 rounds, like 2048 rounds there. So what you can do, you can just include some random timing either into the hash function or just add random delays between the different hashing parts. So this can probably increase the security a bit.
All right, thank you very much. Oh, we got one more? All right, got Nicholas Doria.
Hey.
I wanted to ask as well, so you mentioned that it's very important to have like a precise timing to do this kind of side channel attack.
Yes.
And I already saw like some people concerned about what if I have a web service and that this web service is signing and like does a remote client can use side channel attack to detect that? And so because timing is important, my reaction will be no, it's not possible because like you cannot predict precisely how much time a packet, so TCP packet will flow from the client to the server and vice versa. But some people don't agree with it, so I don't.
Okay, so with the server, yeah, you kind of have random delays on the network that helps. But still, for instance, you're not limited. On the other hand, you're not limited in the number of packets, so you can just get enough statistics to kind of get this timing. So in case of networking, I think that you can just run your tests few thousand times and then get some offset in the timing.
But
what do you think?
In this case, it's like it can also happen on your example where you said like if there is enough randomness, then we cannot decrypt. We cannot use the side channel attack, but like we can say the same point. Like if you make a statistical analysis, it doesn't matter if there is noise. You will be able to filter that out.
Yeah, that's right. So for time, so for measuring time and using time for side channel analysis, and adding random timing doesn't really help. But for instance, if you're using the power analysis, you need to kind of get the triggers of your traces. And here you kind of have a trigger in the beginning of the cryptographic functions. And then if all the multiplications and the additions are happening at the same time, then you can reduce the noise from the power analysis by gathering statistics. On the other hand, if all this stuff is randomly jumping in time, then you add some extra noise so you can't use statistics and differential power analysis to say that, okay, at this place there was always multiplication, so I see that the level goes down. So yeah, this kind of things. Okay. In sense of servers, I think that it will be interesting to talk afterwards how to protect against this.
Thanks a lot.
All right, awesome. Thank you, Stepan.
Thanks. One more thing. So tomorrow we have a workshop where we will try to build our own tiny hardware wallet. So not perfectly secure, not handling most of the things, but it can be flexible enough such that you can actually use it or at least play with it. So I think what I wanted to say. Just come and have fun and also talk to me during the conference. I have lots of other slides that I can't show right now because I don't have time, but pretty nice attacks. So yeah.
All right, great.